Welcome to lesson 2. So today we are going to be doing a meshing, structured meshing for an airfoil. So before we go ahead and do that, there's a few things I just wanted to show you. Every airfoil or every wingo in aircraft flies at a certain speed and certain viscosity, and the airfoil has a certain reference length, which is the chord length of the wing. So a lot of the times as aerospace engineers or research uh, aerodynamics engineers, you will be asked to compute flow conditions, flow field in certain given conditions. And mostly it will be specified through velocity, a free stream velocity at the inlet, and a certain Reynolds number. So let's say we wanted to, our target is that we wanted Mach 0.1, which is incompressible, comes to about 33 meters per second. So I'm going to go ahead and put 33 here. Oh, by the way, this site is called pointwise.com/y+. It's a site to calculate Reynolds number and the spacing of the grid, which everyone has to use before they go ahead and mesh their configuration. So I'm saying my inlet velocity is 33 meters per second. My air density is 1.2 kilogram per meter cube, and my dynamic viscosity is the normal dynamic viscosity in the air, 1.8 into 10 to the power minus 5 kilogram per meter second. And my reference length, for now I'm going to say it's 1 meters, and my desired y plus, or the first cell dimensionless length I want on top of the grid from the airfoil is 1. You'll know what I'm talking about in a bit. So if I go ahead and click output, compute the wall spacing, I get a Reynolds of a wall spacing of 1.1 in 10 to the power minus 5 and a Reynolds number of 2.2 million. Now I want the Reynolds number to be 5 millions. Actually, let's make it 1 million. So what I can do is either I reduce my reference length to 0.5, where I have 1.1 million, maybe 0.45. So it's something you have to just keep changing, trial and error kind of thing. So 0.455. There I go. I have roughly 1 million as Reynolds. Or else I can just keep it 1 and keep changing the viscosity. So it was 18375 before. I'm going to change it to 15375, and it increases. So you go the other way around, 1037. Sorry, 2375. That's still too low. So something like 4 into 10 to the power minus 5 will give you roughly 1 million Reynolds number. And this is the wall spacing that you're going to have to use to capture your boundary layer accurately. So let's go to ICEM CFD again and file, geometry, open geometry. Just jump into the right folder. That's not the one, this one. And these two should be available in the Dropbox folder now. And I'm going to select NACA 12 and create a new project. Yes, and there I go. I have my NACA airfoil. So if I go ahead and click geometry, and I want to see the points too, and the parts too, and these parts are called curves. I'll go and change it into airfoil. Click done. And Okay, so that's the geometry that we want, but we have to measure the chord length before we go ahead and mesh it. So I'm going to be using this option here, measure distance, and control and middle click to middle click and to pan and move around. And I'm going to select this point here and zoom out, pan this side, and select this point here roughly. And it's saying that the chord length of this is 3.5 meters. So we have to go back to that website and put our chord length as 3.5. Now that gives us a Reynolds number of 3.5 million, which is not good because we want 1 million. So we need to scale the geometry, and if you go into calculator, so we want to change something that's 3.5 to 1. So we divide by 3.5 and point. So we need to scale it by this factor. So if you remember what we were discussing in the previous lesson 1, go to transformation tools in geometry button and select everything. Go to scale. Now there is no Z. If I click Z here, there's no Z length, so Z will remain 1. But we want to scale X and Y by the same factor. So we can just copy it or 0.2857. So 0.2857, 0.2857, and from the origin, fine. Click apply. Okay, so now we have an airfoil. If we measure the distance, roughly will be 1. So we can go ahead and mesh it now. We'll be using structured meshing, but we can't compute anything unless we put this wing or airfoil in a flow field. So we kind of want to capture the same kind of curved geometry as in our far field. And if you pan and see here, it's not a sharp trailing edge, it's a blunt trailing edge. So the kind of meshing we use will be a bit different. Realistically thinking, there will be no sharp trailing edges in any configuration or any wings because it is impossible to get that. But sometimes you get these CFD geometries which has sharp trailing edges, and I will discuss with you how to mesh those kind of configurations as well. But for now, let's just concentrate on blunt trailing edges. Okay, so I have my airfoil. I'm going to create points like we discussed before, and I'm going to say this part's name will be far field. Okay, and I know where my airfoil is at. If you're not sure, you can just always go here, show point information. So right click, show point information, and choose a point, and it will give you the location of the point 0, 0, 0. So this point is 0, 0, 0. So the far field has to be at least 20 times 20 chord lengths away. 20 chord lengths, that is 20 times 1, so 20 meters away from the airfoil in every aspect. If, say for example, I'm going to put it 30 chord lengths away, so x30, y30, and click apply and fix screen. Okay, there's my first point. X30, y minus 30 is my second point, and x0 just at the start of the airfoil, Actually, let's put it at x1. Yeah, because that's the end of the trailing edge. So x1 y minus 30 and x1 y 30. And now also we need to make a, I kind of want to get this like the leading edge of the airfoil. I want to get a curve here to properly resolve the leading edge boundary. So what I'm going to do is I'm going to say that my y is 0 and my x is minus 30. Okay, there we go. So we have 1, 2, 3, 4, 5 points there. Now if I go to curves and click an arc from this point, the middle point, and this point, I have an arc there, and I'm going to make a curve here, a curve here, and a curve here. Okay, and even though I called this my far field, I want it to be a bit different, so I'm going to go ahead and change the name. So this is my inlet, and from parts I'm going to say create part by selection, and I'm going to name it as walls, so the wind tunnel, kind of representing a wind tunnel in a computational domain. So I'm going to say this is my upper wall, my lower wall, and this is my outlet. Okay, so now we have an inlet, two walls, and an outlet, and the airfoil just inside. 30 chord lengths away from the airfoil, we have the far field or the wind tunnel domain. But we also need to create a surface, which we are going to call as the fluid zone where the air flows. So I'm going to be selecting all these 1, 2, 3, 4 curves, and it says here surface is not visible. So if I click surface here, I can see the surface now. Wireframe view, I can see the surface. So that's pretty much it for the how to create a domain in which you can capture the flow field. But the difficult part is meshing it. So we are not going to be using unstructured meshing. We want something more professional, something more regular, and we'll be using quotes, which we can do by blocking. So it's the third option here. So I'm going to say create a block. So a block is a way to put a topology on top of the domain and divide it such that we can control the mesh. I'm going to say, okay, I want my blocking to be on top of the fluid zone, and it's not a 3D configuration, so I want a 2D planar blocking. And yes, go ahead and initialize with settings. Fine. So now we got a new section here. It's called blocking, and it's got vertices, edges, faces, blocks, pre-mesh, and topologies. So if I untick blocking, everything disappears. If I untick geometry, you see it's just a square at the moment. It's just covering all the domains. And so the first thing we have to do is associate the outer boundaries. So association is kind of like gluing it to the walls. So I'm going to say associate, not points, but associate these edges, this edge to this curve, these three edges to this curve, and this curve. Okay, when I did that, the color of the edges, so I'm going to untick the geometry, the color of the edges changed to green, which means they're associated to a wall, to a curve. So I'm going to undo that again and show you. You can also use this associate edge, but I think this is going to make things so much easier. Say project vertices. So these vertices are these kind of like node points. And if I say here, okay, associate this edge to this curve, associate these three to these three curves now. You can see it kind of snapped onto the wall. So now I'm going to untick the surface just to make it easier. So now we have something which is quite similar to the outer walls, but still we need to snap it properly to represent the curves. So how do we do that? We can go to this button, it's called Edit Edge and Split Edge. Which method? Okay, you can say I want to use a spline. Fine, and I'm going to left click on the middle. It's snapped onto the, so if I untick the geometry now, it's snapped onto the curve. Here, if I do a spline, it's not going to represent it very well. So I'm going to undo that. I want linear points, linear divisions there. So I'm going to zoom in, pan, zoom in, and just do linear points there. Okay, linear points here. Untick the geometry. Okay, we have something that represents the far field, which is quite good. And untick the surface. But we also need to tell the software how the mesh is going to propagate from these walls up to the airfoil. So how are we going to do that? We kind of have a thing called split block and OR grids. So OR grids are something which is going to come in very, very handy for you. As in, it's one of the things that makes ICEM CFD a great software. So if I go ahead and show you, tick these blocks here. You see there's a block which represents the domain. So what I'm going to do is I'm going to say, okay, I want an OR grid inside this block. And select blocks. I selected this block. And middle click. And it's not around the blocks, it's into the blocks. And I click apply. Okay, so now we have an internal edges. And again, we go back to associate curves. And click this, the inner curves, this, and leave this one for now, and zoom in, untick points, zoom in, and select this part, and the other edge became smaller as well, so we're going to select that edge, the one here which we did not associate. So I'm going to associate that to this curve. Okay, untick surfaces. Right, so we have quite a good representation of what's happening now, except that this is just two lines which doesn't represent the curvature of the airfoil. So again, let's go ahead and move some points on the blocking. So I'm going to move this point here and perpendicular one down here. Okay, and then going to split edge, linear points. Okay, so I made a few points. I'm going to uncheck them, uncheck the geometry as well. So there I go. I have like kind of like a representation of the airfoil. You don't always have to snap it to the airfoil because once it is associated, it captures the shape. But if you use more splits, you get the curvature more correct. So I'm going to do some linear points here as well. So it's all about experimenting on your own using different kinds of splits, but mostly you'll be using spline and linear. Sometimes the software is able to tell how to split it. So if I go ahead and remove these splits on the top edge, and I say here, come back and automatic linear. Oh, that didn't work. Okay, so for some reason that didn't work, but sometimes it automatically splits if it knows the configuration, the geometry well. Anyway, we have represented the. So I'm going to untick the. So I've kind of redrawn the geometry using blocks and edges on the domain, and the problem is we still have an inner block where there will be no fluid flow because the air will be supposedly, like I'm going to untick this box, air will be coming from here all the way here and flowing around the airfoil, not through the airfoil. So we don't need this. So I'm going to go delete block and again delete block and select this one, delete, because I don't need that. Okay, so now that's pretty much the blocking is done. Quite simple, but you can also put other stuff around, which I'll show you later. But let's go into spacing functions. And so when producing the mesh, you have to specify how many nodes you want in how many divisions you want in every edge. And let's say I want on this edge, I want 20 nodes, and on this edge, I want 20 nodes. If you pick 20 here, it's going to put 20 to all the perpendicular ones, all the ones that are parallel to it. So if I go here, it's already 20. If I go here, it's already 20. But these blue edges, the internal edges inside. Oh, by the way, you can just go here, edges, right click, and untick internal edges. And internal edges will disappear. But you kind of need that. So here I'm going to say, okay, I want 20 edges as well. Apply and click pre-mesh. Okay, so we have a grid which is quite good in quality too because it's very orthogonal and stuff. But this is not going to resolve anything, to be honest, because if you go back and check this wall spacing, it says that the height of the first cell, so in y direction, normal to the wall, from here to the first cell, so this is the first cell, so from here to here, it should be 2.3 to the power minus 5 meters, but this is something like 2 meters, which is not good. So I'm going to go and untick pre-mesh and select these edges and say, okay, can you copy the parameters to all the edges that are parallel to it? So you got loads of options here. 20 nodes, and yeah, 20 nodes and the spacings. So now we want to define the spacings. You see this arrow here is something we use to define which direction the edge spacing is defined to be. So this is our spacing 1, and this is our spacing 2. This is our spacing 1, 2, 1, 2, 1, 2. So it's in the direction of the arrow. Not too hard to grasp that concept. And so I don't want my far field spacing to be too big, but I want this spacing to be this value. So I'm going to go and say, okay, like I said, this is spacing 2. If this is spacing 1, this is the spacing 2. So, okay, I'm going to say my spacing 2 will be this value and click apply, and you see how the node divisions has reduced, so that it will be, if I go pre-mesh now, I have refined, I have decreased the wall spacing to the value we need, but still it doesn't capture the roundness of the domain, and it's too coarse to be a good mesh. It needs to have more elements, more cells, more divisions. So what we're going to do is click edge parameters and click this edge. It's going to select all the parallel edges. I'm going to say I need at least about 60 elements here, fine, and 40 elements here, 30 elements there, and click pre-mesh. Okay, so we have something that's a lot better. But if you go outside now, zoom outside, these cells are too big, and we kind of need to reduce it. So I'm going to put about 50 nodes in there, and I'm going to use something called this ratio 2. So how the grid expansion is happening. So if I select here 1.2, that means I want from this cell, from this spacing to this spacing, 20% reduction. So 1.2. If I want 10% reduction, I'll use 1.1. So click apply and pre-mesh. Okay, so we have something that looks so much better. So towards the far field we have big spacings, and as we zoom in we have smaller spacings, and we can accurately capture what's happening in the boundary. So you can use this spacing 2, spacing 1 to control these spacings. For example, if I wanted to match, so it's not really good to have this small spacing, big spacing next to a small spacing. So I can use something called match edge spacing, and my reference edge, so I'm going to untick pre-mesh. My reference edge is this one, and my target edge is this one. Now if you go back and see, it has matched the spacing on this one, but the ratio is still 2, ratio 1, because the arrow is in this direction. So we can change the ratio 1 to be 1.2 to get a better spacing. And click pre-mesh, and now we have a gradual transition. So I'm quite happy with that, but I still want to increase the number of elements here, maybe to 80 or 70. Pre-mesh again. Okay, there we go. Okay, so we have something now. Click dismiss, and we can check the quality of the mesh in terms of, so I went here, pre-mesh quality. So it's not the real mesh yet, because to get the real mesh we have to say convert to unstructured mesh, which then we can use in ANSYS Fluent. But before I do that, I just want to check the pre-mesh quality. So I'm going to click apply and saying, okay, well, nothing is towards the 0, nothing is below 0.8, so I have quite good quality cells. In terms of determinant, I can select other stuff like aspect ratio. Minimum is 1.02, maximum is 916. As long as it's below 10,000 or something, it should be fine, because there's no other way to avoid that kind of aspect ratio, because when you go into the boundary layer, zoom in, you have really long cells with very small y distance. So aspect ratio is like x over y ratio, and there's really nothing you can do about it, because if you go ahead and put like 400 divisions here, and pre-mesh, and check the quality again. Apply. The aspect ratio has reduced to 144, but we have, so pre-mesh info, we have about 59,000 elements compared to before. So that just makes the computation very expensive. So I'm going to go ahead and change it to 100. Apply. Pre-mesh. Quality. Apply. So 510. Before it was 70 elements this way, I think. So this is the structured meshing for an airfoil, and I have uploaded the geometry of a cylinder, which you can use a similar concept, except that this far field or this outer domain will be a circle, complete circle, instead of this semi-arc kind of thing. So I want you to try and try it on your own and see how it goes. Okay, thanks.